In this video, we're going to be talking about angular impulse. So we're going to start from the definition of angular momentum, which is L is equal to I times omega. I is our moment of inertia, which represents how hard it is to rotate something rotationally, cause rotational movement, and rotational displacement. And omega is your angular velocity, which is basically your rotational analog for velocity. So what we're going to do is we're going to take the time derivative. So we have, from Newton's idea of forces cause changes in motion, we can also translate that to rotation and have torque causes changes in angular momentum. So if we take the derivative with respect to time, if we have that I is constant, we can recognize torque as well. So we know torque is equal to I times alpha. So this is equal to torque. So now we can convert this into finite time. So you're going to multiply both sides by dt. So we have torque dt, dl, and we can integrate over time. So our final result is delta L is equal to torque delta T. And this is going to be our golden equation. And our condition for this is that torque has to be constant. So what this means is this is our rotational version of impulse. You can also derive this by looking at the analogs, where we know that force delta T is equal to our change in momentum, which is equal to our impulse. So rotationally, this would be our equivalent. Delta L is equal to torque delta T. So for AP Physics 1, what you should memorize is that our L has to be constant here. A mistake that people usually make is that they say L is equal to torque delta T. That's not right. Our equation is delta L is equal to torque delta T. Only the change in angular momentum depends on torque, not just purely angular momentum. Now let's do some practice problems with this. If you want to follow along, you can go into the description and download the link to these questions. So we have a disk gets a tangential push. A solid disk has a mass m, radius r, and is initially at rest. A constant tangential force F is applied at the rim for a time delta t interval. Find the disk's final angular speed omega F. So if we have our solid disk, we have our mass as m, our radius as r, and it's at rest. So a force is applied at the rim. So that's our force applied. We have that is perpendicular. So this is going to be our lever arm R. So we can use the torque and find the torque that is exerted by this force. We know torque is equal to R times the force exerted times sine of the angle. So we can see here that our lever arm is equal to R. And we know that our force that is exerted is that force applied. So our angle is 90 degrees, so we have sine of 90. Now we can write our torque. So we have delta L is equal to torque delta T that we derived earlier. So because we know that the disk is going to start from rest, we can find LF minus L initial is equal to our torque delta T. So we know that our angular momentum, we can write that as I times omega. So we'll substitute that in here. We have I omega F, and we know that we started from rest here, so we have I times 0, making this whole thing equal to 0. So then we have I omega F is equal to torque delta T. Torque delta T. So now we can substitute in our moment of inertia. We know I is equal to 1/2 mr squared when we have our disk. So here we can just substitute this in. Right here where we have our inertia, we are going to have 1/2 mass radius squared times omega final is equal to RF times our delta t, because we have that our torque exerted is equal to R times F. Sine of 90 is equal to 1, so that was where we got this from. After this, we're just going to solve for omega F. So we are going to divide both sides. We're going to have RF delta t divided by 1/2 mr squared. You can also rewrite this omega F as 2F delta t divided by m times r, because you can just take that 2 and move that to the numerator. So that is your answer for your final angular velocity. So now we have a rod that is hit by tangential force. We have a thin rod of mass m and a length L that is pivoted about one end. So that's your pivot, mass m. It starts from rest, and we have a constant force that is applied perpendicular to the rod at the free end for a time delta t. And we want to find the rod's final angular momentum, or final angular speed, omega F. So we can have that, this is our force. Torque is equal to Fr sine of the angle theta. We can see that the angle is going to be 90 degrees, and this is going to be our force applied. It's going to be applied a distance r from the pivot, so that is your r. And we're going to call this r. This is going to be the length of our rod. So this is just going to be r is equal to L. So we're going to actually say L here. It's going to be our force times L. So that's going to equal to our torque. So that's just FL. So now what we can do is write our delta L is equal to torque delta T. This is your angular impulse, by the way. So we have our change is going to be I omega F minus I omega initial. And we have torque delta T. We have I omega F minus 0, because omega initial was equal to 0 because we started from rest. Now we have torque delta T. So we know that for a rod about one end, that inertia is 1/3 ml squared. On AP Physics, that you won't have to know this, they'll actually give it to you. So you're going to take that inertia and you're going to substitute that in here. So you have 1/3 ml squared times omega final, and you have your torque as well, which we just found right here. So that's going to be your force times the length, and then multiplied by delta t. So we're going to find omega F again. We have that this is equal to LF delta t divided by 1/3 ml squared. So omega final is equal to 3F delta t divided by m times L. That's your final answer. So we can see that our force is going to give our rod an angular impulse. And since the rod starts from rest, the angular impulse is going to become the final angular momentum. So now we have a disk that is slowed by friction torque. We have a solid disk that has a mass m, a radius r, and an initial speed omega initial. The constant friction force torque final acts opposite the rotation for a time delta t. We want to find the final angular speed omega F. We have a radius r and omega initial. So we're looking for omega final. Again, we'll write our angular impulse. We know that the force of friction is going to oppose our rotation. So if we have that, a friction torque is what is going to be analyzed here, that means that the torque that we gain from the friction, that is going to be acting from the friction, is going to be negative torque from the force of friction. So what we can do is write L final minus L initial here is equal to negative torque final delta t. We have I omega final, L is equal to I omega, minus I omega initial is equal to negative torque final delta t. So we can just factor out now. We have an I in both terms, and the I is going to stay the same because we still have the same solid disk. Omega final minus omega initial is equal to negative torque final delta t. So you can divide both sides by your moment of inertia I. So that cancels out, and we just have omega F minus omega initial is equal to negative torque from the friction, delta T, all divided by your moment of inertia. Again, for a solid disk, you have 1/2 mass times radius squared. So you can substitute that inertia in right here, where you have that I in the denominator. And you can also add this omega initial to both sides. You're going to end up with omega final is equal to negative torque from the friction, delta T, all divided by 1/2 the mass radius squared. And you have a plus omega initial here. So you can take this 1/2 and actually move that up here if you wanted to. You would have omega final is equal to omega initial. Just move the omega initial plus to the front. Subtracted by 2 torque from the friction, delta T, divided by the mass times the radius squared. So that is your expression for omega F. So we can see that in this problem, we had our frictional torque that we apply here, 90 degrees from the force of friction, is going to give us a negative angular impulse. So then the disk's angular momentum and the angular speed, they are going to decrease because L is equal to I omega. So then if you have your disk's angular momentum decrease, your delta P decrease, then your angular momentum is your angular momentum, and you have your L is equal to I times omega, right? So then if you have your angular speed decrease, this has to stay the same. So that's why omega has to decrease, because this has to be maintained as something that is constant. So for our next question, we have a platform has a moment of inertia I, and it's initially at rest. We have a small ball of mass m that's moving tangentially with a speed of v, and it hits the edge of the platform at a radius r, and it's gonna stick there. We want to find the final omega f of our platform ball system. So we have a disk again. What we're gonna do here is we know that we have conservation of angular momentum. So we have L initial is equal to L final. So we know that L initial is mvr because we have a also very short collision. That's why we can say that delta L is going to be conserved, because again, delta L is equal to torque times delta T. And if the time is very small, that means that the change in the time is going to be like 1 to 1. It's going to be negligible, which is why we have a conservation of angular momentum. So we can set these equal to each other. We have our radius of our circle is going to be our r, in this case, right here. So then we can also see that we have our total inertia. So this ball, when you throw it and it hits onto the edge, this disk, it already has an inertia, the inertia of the disk, and then this object has the inertia of the object. So in order to find your total inertia total, you have to sum that inertia of the disk and the inertia of the object that you just threw. So that is going to be I plus mr squared, because we have a point mass. This is a point mass, and when you have a point mass, that formula is just mr squared, and it's going to be at a radius from the center, which is our pivot. So we can write our final angular momentum. So L final is going to equal to our total times omega final. So substitute in I mr squared, omega final as LF. So now we can set that equal to our initial. We're going to have mvr is equal to I plus mr squared times omega final. So if we solve for omega final, we just get that mvr divided by I plus mr squared is our answer. And this also makes sense because during this short collision, our torque external is going to be approximately negligible. So that's why, again, we have angular momentum conserved.